Decoding the invisible universe. Welcome. Take a moment and look around you. What do you see? Light, colors, shapes. But here's the thing. You are only seeing a tiny fraction of what is actually there. Most of the universe is invisible to human eyes. Not because it's hidden behind a wall. Not because it's too far away. But because our eyes simply were not built to detect it. Right now, as you listen to my voice, radio waves are passing through your body. Microwaves are bouncing all around you. Infrared radiation is pouring your own skin. Ultraviolet light from the sun is hitting your face. X-rays from space are raining down on you. And gamma rays from distant exploding stars are zipping through you like tiny bullets. And you feel nothing. You see nothing. That is the invisible universe. And today, we are going to decode it. We are going to explore the entire electromagnetic spectrum. From the longest, laziest radio waves, to the shortest, most violent gamma rays. By the end of this presentation, you will understand the single physical rule that connects a children's toy walkie-talkie to a cancer-killing radiation machine in a hospital. Ready? Let's begin. All waves have one job. Let's start with something very simple. A fundamental truth of the universe. All waves have one job. Just one. Transporting energy. That's it. Waves do not transport matter. They do not transport objects. They do not transport you or me. They transport energy from one place to another. Think about a tsunami. A massive wave in the ocean. When that tsunami crashes against a coastline, thousands of kilometers away, did the water from the earthquake zone travel all that distance? No. The water mostly moved up and down in place, but the energy of the earthquake traveled across the entire ocean. That energy moved through the water, and when it reached the shore, it released all that power in a single devastating moment. Now think about something much more gentle. A light wave from a distant star. That star might be millions of light years away. The star itself is not moving toward us, but its energy is. That energy has traveled across the vast emptiness of space for millions of years. And when it finally reaches your eye, a tiny amount of that energy is absorbed by your retina. And you see a point of light. Same job. Tsunami and starlight. Moving energy. Whether it's sound waves making your eardrums vibrate, or seismic waves shaking the ground during an earthquake, or radio waves carrying music to your car antenna. Waves are the universe's primary method for sending energy on a journey. Without waves, energy would be trapped forever in its source. A hot object would stay hot, but it could never warm anything else. A star would shine, but its light would never reach another world. Waves are the messengers of the cosmos, and they never stop working. The great divide in wave physics. Now that we know what waves do, let's talk about the different kinds of waves. Physics has a great divide, a split, a separation into two big families. On one side, mechanical waves. On the other side, electromagnetic waves. What's the difference? One simple thing. A medium. A medium is just a fancy word for physical material. Water, air, rock, metal, plastic. Mechanical waves require a medium. Without to vibrate, they cannot exist. Sound waves are mechanical. If you shout in space, no one hears you. Not because your voice isn't loud enough, but because there is no air to carry the vibration. Earthquake waves are mechanical. They need the solid earth to travel through. Ocean waves are mechanical. They need water. Electromagnetic waves, on the other hand, are diurent. They require no medium at all. They can travel through a perfect vacuum. Absolute emptiness. No air, no water, no matter of any kind. Think about that for a moment. The space between the Earth and the Sun is nearly empty. There are a few atoms here and there. But for all practical purposes, it's a vacuum. And yet, every morning, sunlight travels across that 150 million kilometers of emptiness and warms your face. That's an electromagnetic wave doing its job. So here's the great divide in simple terms. Mechanical waves move energy through matter. Electromagnetic waves move energy through emptiness. And because electromagnetic waves don't need a medium, they can reach us from the farthest corners of the universe. From stars that died billions of years ago. From galaxies so distant that their light is just now arriving. That is why understanding electromagnetic waves is so important. They are our window to the cosmos. Anatomy of an invisible force. So what exactly is an electromagnetic wave? What is it made of? This is where things get really interesting. An electromagnetic wave is actually two waves in one. Two invisible fields. Vibrating together. Perpendicular to each other. The first is an electric field. You can think of an electric field as a region of space wherein electrically charged particle would feel a force. You've experienced electric fields when you've touched a doorknob after walking on carpet and felt a static shock. That zap was an electric field. Discharging. The second is a magnetic field. You've experienced magnetic fields when you've played with a refrigerator magnet. That invisible push or pull is a magnetic field. Now here's the genius part. These two fields are not separate. They are linked. They create each other. When an electric field pulses up and down, it generates a magnetic field. When that magnetic field pulses, it generates an electric field again. And on and on. It's a self-sustaining loop. Imagine clapping your hands together. That clap creates a sound wave in the air. But the sound wave needs the air to keep moving. If you remove the air, the sound stops. But an electromagnetic wave is diurent. It creates its own medium as it goes. The electric field makes the magnetic field. The magnetic field makes the electric field. They keep each other alive. This means an electromagnetic wave can travel through absolute nothingness forever. Unless something absorbs it. This discovery was one of the greatest achievements in the history of physics. A Scottish scientist named James Clerk Maxwell figured it out in the 1860s. He wrote a set of 4 equations that described exactly how electric and magnetic fields behave. And when he solved those equations, he found something unexpected. The solutions were waves. Waves that traveled at a specific speed. A speed that matched the measured speed of light. Maxwell realized something profound. Light is an electromagnetic wave. And so are radio waves. And X-rays. And everything in between. That is the anatomy of an invisible force. 2 fields. 1 self-sustaining loop. Moving forever through the emptiness of space. The speed of light. Let me give you a number. A very important number. 299,792,458 meters per second. That is the speed of light. In more familiar units, that's about 671 million miles per hour, or roughly 186,000 miles per second. To give you a sense of how fast that is, light could travel around the entire Earth 7.5 times. In a single second, light from the moon reaches your eye in about 1.3 seconds. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. Light from the next nearest star, Proxima Centauri, takes over 4 years. Now, here's the astonishing part. Every single electromagnetic wave travels at exactly this speed. In a vacuum, there is no exception. A radio wave from a broadcast tower in your city? Speed of light. The visible light from a lamp in your room? Speed of light. An X-ray from a machine at a hospital? Speed of light. A gamma ray from a collapsing star on the other side of the universe? Speed of light. All of them. The same speed. This constant speed is one of the fundamental pillars of modern physics. Albert Einstein built his theory of special relativity on this fact. Nothing in the universe can travel faster than the speed of light. No information, no particle, no wave. The speed of light is the universe's speed limit. And here's something interesting. When light passes through glass, water, or air, it actually slows down slightly. That's why a straw in a glass of water looks bent. The light slows down when it enters the water, and that change in speed bends the light. But in a perfect vacuum? Always the same. Always. 299,792,458 meters per second. This constant speed is what allows us to measure distances in space. When astronomers say a star is 100 light-years away, they mean it takes light 100 years to travel from that star to us. The speed of light is not just a number, it is a cosmic ruler. The two variables of a wave. Now we have a puzzle. If the speed of an electromagnetic wave never changes, what can change? After all, radio waves are very divergent from X-rays. So something must be divergent between them. The answer is two things, two variables that can change, but only if they change together. The first variable is wavelength. Wavelength is exactly what it sounds like. It is the physical length of one complete wave cycle. If you could freeze time and take out a ruler, you could measure from the peak of one wave to the peak of the next wave. That distance is the wavelength. Radio waves can have wavelengths as long as thousands of meters. That's longer than a skyscraper is tall. Visible light has wavelengths that are incredibly tiny. About 400 to 700 nanometers. A nanometer is 1/1000th of a meter. So visible light waves are smaller than a bacterium. Gamma rays have wavelengths smaller than the nucleus of an atom. The second variable is frequency. Frequency is how fast the wave vibrates. How many complete wave cycles pass a fixed point in 1 second. We measure frequency in units called hertz. 1 hertz means 1 cycle per second. A radio wave from an AM station might have a frequency of about 1 million hertz. That's 1 million vibrations every second. Visible light has frequencies around 500 trillion hertz. That's 500 trillion vibrations every second. Gamma rays can have frequencies of more than 1 billion hertz. Now here's the key connection. Because the speed is fixed, wavelength and frequency are linked. They cannot change independently. If a wave has a long wavelength, it has a low frequency. If a wave has a short wavelength, it has a high frequency. Think of it like a line of people walking at exactly the same speed. If each person takes very long strides, then only a few people will pass you each minute. That's low frequency. If each person takes very short, quick strides, then many people will pass you each minute. That's high frequency. Same speed. Different wavelength. Different frequency. So when we look at the electromagnetic spectrum, we are really looking at two different ways to measure the same thing. Long wavelength means low frequency. Short wavelength means high frequency. They are two sides of the same coin. The rule of inverse proportions. This relationship has a formal name. It's called the rule of inverse proportions. Inverse means opposite. Proportions means how things relate. So inverse proportions means when one thing goes up, the other goes down, and they go down by the exact same factor. Here's how it works. If you double the frequency of a wave, you cut the wavelength in half. If you triple the frequency, the wavelength becomes 1/3 of what it was. If you make the wavelength 4 times longer, the frequency drops to 1/4. It's perfectly balanced. Always. There's a simple mathematical formula that describes this relationship. It looks like this. Speed equals wavelength multiplied by frequency. Since speed is constant, any change in wavelength forces an opposite change in frequency. Let me give you a real example. A typical FM radio station broadcasts at a frequency of about 100 million hertz. That's 100 million vibrations per second. Its wavelength is about 3 meters. Roughly the height of a door. Now compare that to blue light. Blue light has a frequency of about 650 trillion hertz. That's 650 trillion vibrations per second. That's 6,500 times higher than the radio wave. So its wavelength must be 6,500 times shorter. And indeed, the wavelength of blue light is about 450 nanometers. That's 450 billionths of a meter. The math works perfectly every time. This inverse rule applies to all waves, not just electromagnetic ones. Sound waves follow the same rule. Water waves follow the same rule. Seismic waves follow the same rule. But it is especially important for understanding the electromagnetic spectrum because the range of possible wavelengths and frequencies is so enormous, from thousands of meters down to smaller than in atomic nucleus. That's a range of more than 20 orders of magnitude. And the inverse rule governs all of it. The complete electromagnetic spectrum. Now we can finally put everything together. The complete electromagnetic spectrum is exactly what it sounds like. It is the entire range of all possible electromagnetic waves, from the longest wavelength, lowest frequency radio waves, to the shortest wavelength, highest frequency gamma rays. And here's a crucial point. It is continuous. There are no gaps. Every possible frequency exists somewhere. Every possible wavelength exists somewhere. Scientists divide the spectrum into regions to make it easier to talk about. But these divisions are for human convenience only. Nature does not have hard boundaries. One region blends smoothly into the next. Let me walk you through the regions, from longest wavelength to shortest. First, radio waves. These have the longest wavelengths, from thousands of meters down to about 1 meter. They are used for AM and FM radio, television, cell phones, and Wi-Fi. Second, microwaves. Wavelengths from about 1 meter down to 1 millimeter. They are used for radar, satellite communication, and yes, microwave ovens. Third, infrared. Wavelengths from 1 millimeter down to 700 nanometers. This is heat radiation. Every warm object emits infrared. Snakes can see it. Your TV remote uses it. Fourth, visible light. Wavelengths from about 700 nanometers down to 400 nanometers. This is the only part of the spectrum your eyes can detect. Red is around 700 nanometers. Violet is around 400 nanometers. Everything else in between is the colors of the rainbow. Fifth, ultraviolet. Wavelengths from 400 nanometers down to about 10 nanometers. This is the radiation that gives you sunburns. Bees can see ultraviolet light. Flowers have patterns that are invisible to us but glow brightly in ultraviolet. Sixth, X-rays. Wavelengths from 10 nanometers down to about 0.01 nanometers. These can pass through soft tissue but are absorbed by bone. That's why doctors use them to see your skeleton. Seventh, gamma rays. Wavelengths shorter than 0.01 nanometers. These are the most energetic waves in the universe. They come from nuclear reactions, exploding stars, and black holes. Now here's what I want you to remember. Visible light is just a tiny sliver, less than 1/1,000,000th of the entire spectrum. Everything else is invisible to us. But it's all around you. Right now, radio waves are passing through your body. Microwaves are bouncing OU the walls. Infrared is radiating from your skin. Ultraviolet from the sun is hitting your face. X-rays and gamma rays from space are raining down on you. You are swimming in an invisible ocean of electromagnetic radiation. And you have been your entire life. That's the complete electromagnetic spectrum. Seeing the invisible. So why can't we see most of this? The answer is evolution. Human eyes evolved to detect visible light for a very specific reason. The sun emits most of its energy in the visible range. And our atmosphere is transparent to visible light. So it made sense for our ancestors to develop eyes that could see this part of the spectrum. It helped them find food, avoid predators, and navigate their environment. But the universe is glowing in every other frequency as well. Let me give you some examples. The entire universe is filled with a faint glow of microwaves. This is called the cosmic microwave background radiation. It is the leftover heat from the Big Bang itself. It has been traveling through space for nearly 14 billion years. You cannot see it, but a simple radio telescope can detect it. Every object that has any heat at all emits infrared radiation. Your body emits infrared. Your coffee mug emits infrared. A warm sidewalk on a summer day emits infrared. You cannot see it, but a snake can. The sun emits huge amounts of ultraviolet radiation. Too much ultraviolet will give you a sunburn. It can also damage your eyes and cause skin cancer. You cannot see it, but bees can. They use ultraviolet vision to find nectar in flowers. Flowers have ultraviolet patterns that act like landing strips. For bees, patterns we cannot see at all. Exploding stars, called supernovae, emit enormous amounts of X-rays and gamma rays. Black holes shoot jets of X-rays across space. You cannot see any of this, but space telescopes like the Chandra X-ray Observatory can. And when they do, they reveal a universe that is violent, energetic, and incredibly beautiful. So here's the truth. We are mostly blind to the universe. But we don't have to be. With technology, we can see the invisible. Radio telescopes let us see the radio sky. Infrared cameras let us see heat. Ultraviolet detectors let us see the sun's hidden storms, X-ray and gamma ray. Telescopes let us see the most violent events in the cosmos. Each new technology opens a new window on the universe. And every time we open a new window, we discover something unexpected. That's why the electromagnetic spectrum is so important. It is not just physics. It is our map to everything that exists. The power question: red or blue? Let me ask you a question. A simple question with a surprising answer. Which carries more power? Red light or blue light? Think about it for a moment. Both red light and blue light are electromagnetic waves. Both travel at exactly the same speed. The speed of light. But they have divergent wavelengths and divergent frequencies. Red light has a longer wavelength and a lower frequency. Blue light has a shorter wavelength and a higher frequency. So which one carries more energy? The answer is blue light. Blue light carries more energy than red light. Here's why. Remember the rule of inverse proportions. When frequency goes up, wavelength goes down. But something else goes up too. Energy. The energy of a single photon, one particle of light, is directly proportional to its frequency. That means if you double the frequency, you double the energy. If you triple the frequency, you triple the energy. Blue light has a higher frequency than red light. So each blue photon carries more energy than each red photon. Let me put some numbers on this. Red light has a frequency of about 430 trillion Hz. Blue light has a frequency of about 650 trillion Hz. That's about 1.5 times higher. So each blue photon carries about 1.5 times more energy than each red photon. Now extend this logic across the spectrum. Ultraviolet has a higher frequency than blue light. So ultraviolet photons carry even more energy. X-rays have a higher frequency than ultraviolet. So X-ray photons carry more energy than ultraviolet. Gamma rays have the highest frequencies of all. So gamma ray photons carry the most energy of any electromagnetic wave. At the other end of the spectrum, radio waves have the lowest frequencies. So radio photons carry the least energy. That's why radio waves are harmless. They simply don't have enough energy to eject your atoms. So here's the rule. Write it in your mind. Higher frequency equals higher energy. Lower frequency equals lower energy. That's not an opinion. That's not a theory. That is a physical law. It is described by a simple equation. Energy equals a constant called Planck's constant multiplied by frequency. This equation is one of the most important in all of physics. It connects the wave nature of light to the particle nature of light. It tells you exactly how much energy a photon has. And it explains everything from why red lights are used in darkrooms to why gamma rays are so dangerous. So remember, red is low energy, blue is higher energy, ultraviolet is even higher, X-rays higher still, and gamma rays are the highest of all. That's the power question. And now you know the answer. When energy becomes dangerous. So if higher frequency means higher energy, at what point does light become dangerous to living things? There is a threshold, a boundary, a line in the spectrum. This boundary sits between ultraviolet light and X-rays, at an energy of roughly 10 to 124 electron volts, depending on the material. Below this boundary, non-ionizing radiation. Above this boundary, ionizing radiation. Let me explain the divergence. Non-ionizing radiation has enough energy to make atoms and molecules vibrate. It can heat things up. That's how a microwave oven works. The microwaves make water molecules spin and vibrate. And that vibration creates heat. Non-ionizing radiation can also cause chemical changes. Too much ultraviolet from the sun can give you a sunburn. That's damage. But it's not ionization. It's mostly heat and broken chemical bonds that the body can repair. But non-ionizing radiation cannot knock electrons out of atoms, it simply doesn't have enough energy. Ionizing radiation is die-errant. Ionizing radiation carries so much energy that it can do something dramatic. It can literally rip an electron away from an atom or molecule. That process is called ionization. And it changes everything. When you ionize an atom, you turn it into an ion, a charged particle. That atom's chemical behavior changes completely. It becomes reactive. It can form bonds it wouldn't normally form. It can break bonds that were stable. Now imagine that happening inside your body, inside your cells, inside your DNA. That is why the boundary between non-ionizing and ionizing radiation is so important. Below that boundary, radiation is generally safe. Above that boundary, radiation is dangerous. X-rays are ionizing. Gamma rays are ionizing. Some extreme ultraviolet is ionizing. Radio waves are not. Microwaves are not. Visible light is not. Infrared is not. Most ultraviolet is not. So the next time you get an X-ray at the dentist, remember, those X-ray photons are carrying enough energy to knock electrons out of your atoms. That's why the technician stands behind a lead shield. That's why you wear a lead apron. The lead absorbs the ionizing radiation before it can reach your body. Crossing the ionizing boundary changes everything about how radiation interacts with living tissue. And understanding that boundary is key to understanding the danger and the medical power of high-energy electromagnetic waves. Ionizing radiation physically breaks cellular structures. Let me now tell you exactly why ionizing radiation is so dangerous. And I mean the physical, molecular reason. When an ionizing photon, an X-ray or a gamma ray, hits a molecule in your body, it transfers its energy to that molecule. If it transfers enough energy, it can eject an electron from the molecule. That molecule is now an ion. It has a positive charge because it lost a negative electron. This might sound like a small thing, but it is not. A molecule that has been ionized is chemically unstable. It wants to react. It will grab electrons from nearby molecules. It will break bonds. It will form new, unwanted bonds. Now consider the most important molecule in your body, DNA. DNA is the instruction manual for your cells. It is a long, delicate chain of chemicals that tells each cell what to do, when to divide, and how to build proteins. If an ionizing photon strikes a DNA molecule, several things can happen. First, it can break one of the strands of the DNA double helix. That's called a single-strand break. Your cells have enzymes that can usually repair this kind of damage. Second, it can break both strands of the DNA double helix at the same time. That's a double-strand break. This is much more serious. The cell has a harder time repairing double-strand breaks. And if it repairs them incorrectly, the genetic code can change. Third, the ionizing radiation can create free radicals, highly reactive molecules that then go on to damage DNA indirectly. This is actually how most radiation damage happens. The radiation hits a water molecule, turns it into a free radical, and that free radical attacks the DNA. So what happens to a cell when its DNA is damaged? If the damage is minor, the cell repairs itself. This happens thousands of times every day in your body. If the damage is severe, the cell might die. This is actually what doctors want when they use radiation to treat cancer. They aim ionizing radiation at the tumor, and the cancer cells die because their DNA is shredded. But if the damage is in between, not minor enough to be repaired perfectly, not severe enough to kill the cell, then something dangerous can happen. The cell survives, but with mutated DNA. And if that mutation ejects the genes that control cell division, the cell might start dividing uncontrollably. That is cancer. This is why ionizing radiation is a carcinogen. This is why nuclear accidents are so deadly. This is why astronauts who are exposed to more cosmic radiation have a higher risk of cancer. And here's the cruel irony. The same physical process that makes gamma rays deadly also makes them useful. Doctors use precisely aimed gamma rays to kill cancer cells. The gamma rays damage the DNA of the tumor cells so badly that they die. Meanwhile, healthy cells around the tumor are spared as much as possible. So ionizing radiation is both a weapon and a tool, a destroyer and a healer. But the physics is the same in both cases. Enough energy to knock an electron out of an atom. That's the threshold. That's the danger. And that's the power. The energy continuum. Let's go back to where we started. A harmless radio wave and a deadly gamma ray. What is the real difference between them? Not their nature, not their type, not some magical property. Only frequency, only wavelength, only energy. The radio wave has a long wavelength and a low frequency. Its photons carry very little energy. When a radio photon hits your body, it passes right through you as if you weren't even there. It doesn't have enough energy to interact with your atoms. It is harmless. The gamma ray has a short wavelength and a high frequency. Its photons carry enormous energy. When a gamma ray photon hits your body, it slams into your atoms and molecules like a wrecking ball. It knocks electrons loose. It breaks chemical bonds. It damages your DNA. It is deadly. But here's the profound truth. They obey the exact same physical laws.